So, we are discussing about the Bohr model of an atom, Bohr model or structure of an atom. So, what we have seen that energy expression En equal to minus mz square e to the power 4 divided by 2 n square h cross square. And in terms of, so that is the energy levels. Energy levels is inversely proportional to energy level, it is inversely proportional to n square, 1 by n square is proportional to 1 by n square, right. So, if we draw energy level n equal to, so n equal to 1, 2, 3 all integer. So, if I draw n equal to 1, then n equal to 2, n equal to 3, n equal to 4. Okay. So, then basically, so this way okay. So, basically you will get, so n equal to basically we tell the infinity. Okay. So, from here one can find out the energy E1, E2, E3, E4, okay, like this. So, for hydrogen atom, if we put n equal to 1, then E1 you will get, so E1 you will get 13.6 minus 13.6 eV. E1 for a hydrogen atom, E1 you will get minus 13.6 electron volt. Okay. Then what will be the E2? What will be the E2? So, it is from here itself you can tell E1 equal to, so n equal to 1. So, that means this value is 13.6 minus 13.6 minus 13.6 divided by n square. So, n equal to 2, so it is divided by 4. So, it basically you will get minus 4 means 312, honestly minus 3.4, sometimes 3.39 also people write electron volt. Okay. Similarly, E3 you will get, so 9, so 1.1 then 9 4 46, so 5, so 5 1 electron volt. Okay. So, this way one can find out the energy. Then, so you can see the separation between two energy level, it is decreasing, and this transition from one energy level to the another energy level. So, this separation. So, here you can see this say E2 minus E1 or E1 minus E2. From here one can find out the separation del E equal to E2 minus E1, okay, and that will be how much? So, I think it will be 10.2 electron volt. Okay. So, this energy difference you will get as a radiation, and if you calculate corresponding wavelength, so this should be one H alpha line, this should be H alpha line. So, this wavelength we have seen, I think 6563 angstrom, 6563 angstrom. Yes, probably I have written correctly. So, this energy, from this energy one can find out this wavelength. So, you know this energy equal to, so that del E equal to H nu, okay, H nu equal to H C by lambda, okay. So, lambda equal to H C by del E, okay. So, actually taking the difference of energy level, whatever the wavelength was achieved, so that one was slightly, so it was not the same wavelength whatever observed experimentally. So, here I have written correctly, but its value was slightly different. So, actually this one has to take mu, reduced mass, m has to replace mu as I mentioned, and then you will get this value. These value are correct value, but if you take m, then this value slightly changes and E1 E2 slightly changes, and corresponding this del E will not be 10.2, it is slightly different, and that spectral line radiation, so it will be slightly different than the experimentally observed wavelength. Okay. So, from there basically this reduced mass concept came, that I have mentioned, that if the nucleus is not at rest, okay, so then one has to consider the motion of the electron and the nucleus together with respect to the center of mass. So, since experimentally it was not fitting with this Bohr model calculation, so to then this when this reduced mass concept was introduced, and finally result from the Bohr energy, and that was the same, that was the that result was same with the experimental result. Okay. So, another thing was that reduced mass concept that is required. So, from another spectral line in hydrogen atom, it was found that say, as I mentioned, this H alpha line, H beta line, etc., H gamma, H delta, and then series limit, Okay. So, each line, it was seen, initially it was not observed, but later on when this spectra was observed in powerful spectrometer, resolution was better. Resolution is nothing but the how to resolve, how to see, how to separate two close spectral lines. Their wavelengths are very close, separation is very small. Okay. So, if one can resolve these two spectral lines with small difference of wavelength, so then we tell we define the resolution of this instrument in terms of this separation. So, how small this separation? If smaller the separation, the resolution of the instrument are better. Okay. So, in higher resolution, it was seen that this each spectral lines, bright spectral lines, is associated with a faint line, Each spectral line was associated with a very weak faint line, okay, very weak or faint spectral lines. So, what is the source of these lines? So, again that is basically because of the reduced mass, and these spectral lines was coming from the isotope of hydrogen, that is deuteron. Isotope of hydrogen, that is deuteron. I think yes, I do not need them. So, to get this one, so basically isotope was discovered, from this isotope of hydrogen, that is deuteron, and deuteron, this hydrogen, it has atomic number 1. So, it has 1 electron and 1 nucleon, that is proton, but in deuteron it has 1 electron and 1 proton and 1 neutron. So, its mass is double, charge is same, but mass is double than the hydrogen atom. Okay. So, now, so mu is basically what? M by m plus m. Okay. So, this is the nuclear mass and this is the electron mass. So, this we can write 1 by m plus 1 by m, right. Now, for spectral line we used basically nu bar, right. What was that? Nu bar was as I remember, so 2 pi square mu z square e to the power 4 divided by C h cube and then 1 by n1 square minus 1 by n2 square 1 by n2 square, okay, and this is basically mu, this is mu. So here we used to write, I think this we can write as a Rydberg constant for hydrogen, and then into, so for hydrogen it is z equal to 1 has to take, so z square, okay, z equal to 1 is taken for in this RH, so z square, okay. So for so in case of deuterium z is 1, so Rydberg constant looks same, but it is not the case, because if you consider, so this this now mu is different. So mu one has to write here h, so one has to write, I have to, what I have to do this, so in Rydberg constant mu is there, so I will divide it by mu, okay, h into mu h. So yeah, into mu h. So this I can write, okay, and this part is there, this part is there. Now here, so whatever the this in case of mu h, so for now if I consider this mu d for deuterium mu d, so mu d and mu h, so what I can do from here, I will get 1 by m, that is common, m is common for hydrogen and this deuterium, but this is different. So here I have to write 1 by 2m, okay. If m is the mass of the proton, in deuterium 1 proton and 1 neutron, so if we consider the same mass of both, so here it will be 2, okay. So whereas mu h is 1 by m plus 1 by 2m, okay, sorry 1 by m. So here you can see that in case of mu d, this is smaller, this is half, basically half than this one, it is half than this one, okay. So whatever this value, this is half, this is smaller, so this is smaller means mu d will be, this is smaller, so mu d will be higher, mu d will be higher than mu h, right, because in denominator this is whatever this value, this is higher value and this is lower value, okay. So its lower value in denominator. So, mu d this will be higher than this mu h. Okay. So, when E n, so mu, when it is mu h or mu d, so this is higher value. In this case, the separation in case of wave number. So, what you will get? So, this is higher value, this is higher value. So, this value will be higher, this value will be higher. So, nu bar will be higher for nu d, nu bar will be higher. So, what is nu bar? 1 by lambda. So, nu d, nu bar d is higher. So, lambda will be smaller. So, lambda for d will be smaller than corresponding lambda for mu h. Okay. So, it will come at lower side. So, that is why at lower wavelength it is lambda. Okay. So, this always at lower wavelength there is a faint spectral line associated with each spectral lines of hydrogen. So, these spectral lines is basically is from deuteron. So, hydrogen, in hydrogen always some percentage of deuteron is there in hydrogen gas. So, one cannot avoid the presence of deuteron, but it is very 1 to 3%. So, that is why the spectral lines are weaker, and later on intentionally the increasing the deuteron ratio in hydrogen gas. So, it is seen that this faint line become brighter, because now the ratio of the hydrogen gas and the deuteron. So, this mixture, now this ratio is higher. So, that is why these lines become brighter than the earlier one, brighter than the earlier one. So, that is, so this again, this means basically this reduced mass is very, that was the correct, that was the proper correction to the initial Bohr result, where initially it was taken. So, later on it was properly, it was replaced by mu, and that is the presence of deuteron in hydrogen gas as a isotope. So, that was determined from the spectral lines of hydrogen. Okay. So, this reduced mass correction was given to the original Bohr expression, energy expression, and that helps to explain, that helps to get the correct wavelength of the spectral lines of hydrogen atom, as well as that helps to discover the presence of deuteron in hydrogen gas. Okay. So, then from here, as I drawn the energy levels. So, Bohr model is telling that energy levels are discrete, and from the transfer of electron from one level to the another level, or due to jump of electron from one energy level to another energy level. So, we are getting radiation and corresponding spectral lines we are seeing right. So, there is a nice experiment which gives the direct confirmation of the discreteness of the energy levels in atom. Okay. So, that experiment is called Franck-Hertz experiment, and it is very famous for the direct. I think I will keep it. So, Franck-Hertz experiment, okay. And this is very simple and nice experiment, and it gives this the direct evidence of the presence of the discrete energy level in the atomic structure. Okay. So, this Bohr model is basically, it was given for hydrogen atom. So, for one electron system, but it is valid for any atoms. This concept is valid for any atoms. It's not directly this formula is not directly valid for all atoms, means multi-electron atoms, but the concept of discreteness of energy levels in any atoms. Okay. So, that concept is valid. So, that means the energy levels of in any atom, it is single electron or multi electron, they are discrete. Okay. So, one experiment was designed by Franck and Hertz. So, what was that experiment? There was a tube, and it was kept at low pressure, means it is evacuated and kept in low pressure. Okay. So, there is a cathode, and there is a anode. It has some hole perforated, it has some hole. So, this is cathode, this is anode, and there is a plate collector, So, this cathode emits electron, Okay. So, one power was given, say. So, what I will do, let us take voltage divider. Okay. So, this was connected here. So, this side is basically plus and this side minus. So, this was connected here. So, this basically is minus. So, it's a minus cathode, it's plus. So, this is positive bias, and then here plate, here it is given it's a negative. So, this is positive, so it's connected with positive. Okay. So, and here one ammeter is attached. Okay. So, it can measure the current, and this voltage difference between, I think here one voltmeter, I think this, yes, here one voltmeter, here one voltmeter V is connected. is connected, and here another voltmeter is connected. So, I think I will not connect this way. So, this is positive, this positive. So, here one voltmeter, I think this is V1 I will give. So, this changing this one, this voltage is between these two, and here his current is flowing due to the same positive here. Okay. So, this positive and this one is negative. So, this here another voltmeter is connected, it is V2. Okay. Okay. So, this is the experimental arrangement. Now, you see this voltage difference between these two. So, cathode negative, this positive. So, electron emitted from this cathode, it will be accelerated. Okay. It will be accelerated and it will move towards the anode. So, its energy will be, its energy E1 will be EV1, okay, energy of the electron. Now, since there is a hole in this anode, so electron will pass through it. When it will pass through it, so when electrons are reach here, so its energy will be EV1, okay. And when it is coming in this region with EV1 energy, okay, so it will reach to the collector if this V2 is basically retarded potential, V2 is retarded potential, V2 is retarded potential. Okay. So, what will happen? This electron will reach here if EV2 is less than EV1. Okay. This is retarded potential. It will, so whatever electron is coming with this energy, so it will be repelled by this plate, but it can overcome if this energy is higher than this, okay, or V2 is less than V1, okay, V2 is less than V1, okay. So, generally this retarded potential is kept smaller than this V1, okay. So, now, so electron will reach here, so electron is coming here, so it will circulate, so you will get current. Now, if I plot this current, current I, and if I change the voltage V1 keeping V2 fixed, smaller value than the V1, okay. Now, if I change this V1, so that we can change here. So, this current, if I note down the current and plot it, so Franck and Hertz, they are getting like curve like this. Okay, like this. Okay, it will move away. Okay, so I think this I can make slightly smaller. Okay. So, okay, this way it was. So, some peak here, you can say peak, it is not peak, current is increasing, voltage is increasing, current is increasing, more and more electrons are reaching there. So, then it is reaching at the highest value, then suddenly drop, current suddenly drop from peak value to this smaller value, and then again if we continue to increase this one voltage, so again it is increasing, then at another voltage suddenly drops. So, why it drops? So, basically here what happens is mercury, initially any gas can be taken, but in the original experiment mercury gas was taken, mercury gas, okay. So, that means mercury atoms are there, and in low pressure mercury gas was taken. So, mercury atoms are there. What happens? So, electrons are moving and they collide with mercury atoms, but since mercury is very heavy, mercury atoms are very, mass is very heavy. So, there was a elastic collision, okay, elastic collision, and without losing energy they can move and reach to the plate. Okay. Now, at a particular voltage V1 say, so this energy when E1 equal to EV1, so then suddenly current drops. So, this value was seen that it was 4.9, it is a 4.9 electron volt. Okay. And then again it was the second drop came, it was I think 6.7, second drop came, it was 6.7, most probably yes, 6.7 electron volt, it came 6.7 electron volt. Okay. So, this peaks was coming. So, then it was why it happens, and then simultaneously this spectrum, simultaneously the spectrum of this helium gas was also studied and found that exactly corresponding this wavelength corresponding this energy, okay, is found in that, in the spectral lines of the mercury gas. Okay. So, what happens? So, when electrons are moving, there is a elastic collision, but when the energy of this electron is close to the energy level, close to the separation of the energy level of mercury, then this mercury atoms, it absorbs that energy, okay. It can absorb fully or partly, okay. Then this electron will lose the energy. So, its energy whatever they absorb, it absorbs, that is separation of the energy level. So, the energy of the electron it will be now less by that amount, whatever it will be less by that amount, say it was energy separation was E. Okay. Now, this energy of the electron it will be reduced by this amount. So, now this energy it will be less than the retarded potential energy EV2, and that electron cannot reach here, okay, cannot reach here. That is why this retarded potential is used. It may have some energy after losing this energy. So, if this retarded potential is not there, it could reach there. Okay. So, this now this energy of this electron after this partly transferred to the mercury atom, now that energy is less than the retarded potential energy and it cannot reach to the collector or plate, and thus it is just suddenly decrease. So, again if you increase this energy, so it is going to the to the second level, okay, to the second level. So, from this experiment it is, so one can think of energy level in the mercury atom, and the separation of this energy level it is 4.9 electron volt, separation of this energy level with respect to the ground state, that is 6.7. Okay. So, similarly other energy level one can find out. Okay. So, this the direct proof of the existence of the discrete energy level in atom. So the Franck-Hertz experiment is very simple, it is very simple, but this gives first direct evidence of the discreteness of the energy level in atom. So, I will stop here. Thank you.